Question. All right. So before we get started, any questions about the homework?
Just number 8 on 8.4.
Okay. So 8 on 8.4. Notice I went ahead and pushed 8.5 was due tonight at midnight. I went ahead and pushed it to Monday at midnight because I didn't get through it all yesterday. So we'll finish out 8.5 today and then do 8.6. All right? So 8.4, number 8. Let's look at this one. Okay. So it's multiple to 5 parts, okay. All right. So here's 8.4, number 8. Starts off, it says, television commercials most often employ females or feminized males to pitch a company's product. Research published in a certain magazine revealed that people are, in fact, more attracted to feminized faces, regardless of gender. That's also true with voices. That's why Siri on the iPhone is a female and not a male, because people are more receptive to a female voice. Probably has to do with the whole mother instinct. In one experiment, 40 human subjects viewed both a female face and a male face on a computer. Using special computer graphics, each subject could morph the faces until they attained the most attractive face. The level of feminization was measured. So notice our unit is in terms of percentage. All right, so that's something we're going to have to notice whenever we enter our test statistic in. And as we're going through this problem, we have to remember our units here. Our units are a percentage, which is kind of a mixing of mu, right, our mean or average, and the proportion. Our unit here is percentage for the mean. All right, so it says, the researchers used this sample information to test the null hypothesis of a mean level of feminization equal to 0%. So it says, identify the test statistic. First of all, is this a large or a small sample? Large, right? Because n is greater than 30. Right here it says 40 human subjects. Right? So therefore, we're going to be using the large sample. What I'm going to do right here is look at the answer, and then we'll work back towards it. Because I'm able to do this, click, and show the completed problem. So it gives us a test statistic of 2.26. So let's see if this makes sense. All right, so let's plug it in to our formula. So let's see if we can come up with this value. So it's just asking for the test statistic, and it's going to be Z. And let me go to this one so it's a little bit bigger. There's our X bar. What's our mu for this problem? 0, right? Good job. Mu is 0. So our Z is always equal to X bar minus mu over S divided by the square root of n. So that implies that's equal to, what do we have? So if I change it to a decimal, then I have to change everything to a decimal. If I leave it as a percentage, I have to leave everything as a percentage. So your units have to be equal. So let me punch this in and then see if it works out, or if we have to actually mold it into a decimal problem. So we have 8.6 minus 0 divided by s, which in this case is 32.4, divided by the square root of n, which in this case was 40. Now what's important is that our x bar and our s are definitely in the same unit. All right, so our x bar can't be a decimal and our s be a percentage. We have to keep them in the same unit. So let's punch that in our calculator. What do we get there? So it's 8.6 divided by, go ahead and open a parenthesis. Just get used to putting that whole denominator in a parenthesis. 32.4 divided by the square root of 40. And I'm not coming up with exactly the same thing as what the book is giving us. They attain most attractive. So I think it's a unit issue is what's going on here. Let me look at this and make sure. Did it change my values? Oh, it did. That's what happened. Notice when I click Show Completed Problem, it gives me a different X bar and a different S than what I have listed here. Look, this X bar was 8.6 and 32.4. So let's go ahead and just use this. So I'm not going to use the Word file. So I'm going to go back and change it because it updated the problem. So I'm going to change my X bar and my S. I didn't notice that before I punched it in. N stays the same though, right?
N's 50.
Oh, N's 50 now, so it changes as well. So that's something we got to pay attention to as we're doing this homework. Because it's an easy error to make. So 10.8, now it's 33.8, and then 50. So let's verify that this equals 2.26. All right, so we have 10.8 divided by... All right, so that makes sense. And I know what kind of happens with these is you'll read the view and example and it'll have different values than the question will have. And sometimes you mix and match some of the values. So that's just something to pay attention to as we go through this. Now hopefully if I click uncompleted problem, it won't change it. Let's see. Yep, and it changed it. Every time it's going to change it. So let's do it again. This is just good practice. Let's do it again for another z-score. So I'm going to do it now with these points. This is good practice that you get the values that I'm coming up with. Because this is very important that we can put the right z-statistic. Because if we don't find the right test statistic, then there's no way we can be right on the problem. So I'm going to change this back to 8.9. Change this to 30.7. And did my n change? It's 50. So let's do it for this one. Divided by, open parenthesis, 30.7 divided by second square root of 50. So this time I got 2.05 for this set of data. Is that what you guys got there? All right. Now I'm not sure if it wants us to put exactly. Here we go. Okay. Okay. So for this, what type of tail test is this going to be? What do you guys think? What's the mean here? 0%. So does it make sense to go left of 0? No. It doesn't make sense for my alternative to be not equal to 0 in this particular problem. So my null, which was given to me, is mu equals 0. So my HA would be mu is greater than 0. It doesn't make sense to say not equal because that would involve being less than 0, which doesn't make really any sense. So this is going to be a one-tailed test. which is very important when we're finding the p-value, right? So what it wants for the p-value is it wants to know the area under the curve that's to the right of 2.05. So here's my z statistic. So it wants this value. Notice it hasn't given us an alpha, right? It hasn't told us to find the rejection region because it hasn't given us a value for alpha. So the p-value is going to be the values to the right, the area under the curve to the right of 2.05. So it's going to be 0.5 minus whatever the area is in the circular colored region, right? So let's go look at our chart for 2.05. I think I can pull the textbook up. I think in this new setup it allows you to open the textbook without closing the homework assignment. No, it doesn't. So I'm just going to look at the textbook that I have here in front of me. You guys will just have to believe me if you don't have one. So 2.05 is 0.4798. Do you guys agree with that? For you to use that habit, 0.4798. All right. So 0.4798. So we need to find the difference between those two. 0.5 minus 0.4798. And it says round to how many decimal places? 3. So that would be 0.020 or 0.02. If the test is one-tailed, so now I don't really want to click to view an example yet. Let's think about it a little bit more. So if it was double, if this was in fact a two-tailed test and I was misinterpreting it, I would just double this portion, right? Because it would just, then it would be the negative 2.05, which this question, I don't see how it would really make much sense to be two-tailed. Well, let's just double that number. So I'm going to take my previous z-score and just do times 2. I get 0.0404, which rounded to 3 decimal places would be, and it is two-tailed. Let's look at why. Oh, here's the, so let's read this. The alternative hypothesis, denoted HA, is a theory that contradicts the null. This usually represents the values of a population parameter for which they want to gather evidence. Bless you.
Because they said not equal to?
Well, this says not equal to. Does it say not equal to in the question? It doesn't, right? So this, to me, I could argue that this would be greater than 0. Now, I wouldn't give you this question on a test. I would definitely make it a lot more, a lot easier to see whether it was a 1 or a 2-tail. But to me, it doesn't make really any sense. I guess that would be, if X went negative, it made the face more masculine, I guess would be the interpretation here of this problem. But to me, if I was building it, I would only have it as a one-tailed test. So I'd really like to see the books. What is their argument for it being not equal to rather than just greater than? Because we're working towards feminization, which I guess a negative percentage would make sense because it would make it more masculine. So this is kind of a funny problem. Like I said, as we've went through Chapter 8, this is the hardest part, really, to these problems, is setting your null and alternative hypothesis up correctly, which I didn't do, right? I did it incorrectly. As the book is stating it, as I read it, though, I would think that greater than would make more sense. Okay, so that's the argument there for this. I'm not convinced that it's not equal to, but we'll go with what the book's telling us. Okay? So let's go ahead and just make it a two-tailed test. So we'll call it a not equal to. So then here's negative 2.05. I definitely looked at this problem, but I didn't, I guess I didn't get quite that far into it when I was researching this stuff, when I built these homework assignments. Because I could almost have a question for Pearson right here about that. because it says most attractive, the level of feminization, so I guess it could turn negative.
Because they did mention the masculine.
Masculinity, right? So if it goes negative, then it's more masculine. Yeah, this is
At that point, though, leads you to believe that 0% would be no alteration at all.
right. Exactly. So it doesn't make sense to me to talk about anything that's less than 0%. If I was building this, or if I gave you this on a quiz or something, I would definitely expect greater than 0. Makes more sense for the alternative. But let's keep going. And that's probably what the question was more about on this problem, huh? Was the setting up the null and alternative. So it says the researchers used this sample information to test the null hypothesis of a mean level of feminization equal to 0. What it should say is against not being 0, right? You know, if we had those extra 4 words in this part A that said against it not being 0, then it would explicitly be not equal to. So really, I don't think we're given quite enough information to explicitly define that HA. So this isn't the greatest problem in the world, but now we can still answer it. You know, and I think as you go through it and you noticed it was wrong on the first part, the view and example definitely pushes you in the right direction. But I could argue that it's incorrect. Well, let's keep going. Does everybody understand where this p-value came from? So it'll just be this value times 2, right? It's going to be our p-value. So it's both of the lined regions. All right, so let's keep going. Interpret the p-value. So assuming mu is 0, it's a weird problem. Because now it's just telling me less than or greater than. It's not giving me or equal to. But what would we do based on the z statistic? What's this value right here? Is this greater than the mean or is it less than the mean? 2.05. Greater than the mean. So it would be, it'd definitely be either A or D, right? Because the mu has to be 0, not 8.9. So it's either A or D, and it is, which one? D, right? Because we have greater than. Assuming the mu is 0%, the p-value is the probability that x bar is greater than 8.9% in magnitude. Because the reason the answer to this is greater than, bless you, is because our z statistic is a positive value. It's above the mean. All right? So same thing. So let's do it again for different values. Bless you. Do it again for different values. But now I'm going to go ahead and interpret it as not equal to. So let's go ahead and erase. I'm going to write that a little smaller so I can put it all in one line. Z equals. So notice our mu does not change right here. The only thing that changes is our mu and our n doesn't change. The only thing that changes is x bar and s. So we have x bar minus mu divided by s over square root of n equals 14.1 minus 0 over 23.6 divided by the square root of 50. And what does that equal? Bless you. Oh, you guys got it already? Okay. Doing good, all right. Divided by, over parentheses, 23.6 divided by second square root of 50. What do we get there? 4.22. So that's our test statistic, 4.22. So that's way above the mean, right? That's a severe outlier. I mean, that thing's really far away. So based on that test statistic, we would assume that the population mean is much greater than 0. Much greater. And then finally find the p-value. Let's interpret the p-value as a two-tailed test. So our chart doesn't even give us 4.22. So what do we do here?
0.5 minus.
Minus 0.5, basically.
4990.
Well, but even that is just for 3.0. So let's see what it tells us. Everybody does realize what we're looking for is the area of the slashed regions, right? Does everybody realize that? Which is going to be, I mean, at 3.09, according to the book, is basically all of the area, or half of the area, right? So I would assume this is 0.5 minus basically 0.5. So I wonder what it's going to do if I just put 0. There's absolutely no area. And the reason is because this value is so far away from the mean. Because look, even if I go look at other Z charts online, because our book only goes out to what, 3.09 is the biggest value, right? That chart shows? Yeah, 3.09 is the biggest value. Let's just look at some other charts. Let's go to images and then pick a good one. Yeah, one that's going to be a little clearer than that. Because here's one that goes to negative 3.49, and look what it is. Can you guys see that? Yeah, and the way this one works is it basically shows the area to the left of the Z value. And wouldn't you guys, negative 4.22 is even farther left than that one. And since we're only rounding this to 3 decimal places, what's this number rounded to 3 decimal places? 0. So that means there is no area to 3 decimal places to the left of even 3.49. So of course there's not going to be any area to the left of negative 4.22. Really, anything over about 3.1 is essentially 0. Because look at 3.1 here is 0.001. You guys see that? .001. So that's not quite 0, but it's dang close. And as we get farther away from the mean, notice how the values get farther and farther away from 0, right, as Z gets smaller. Because this chart is written the other way around, right? See how this one builds up as you go this way? And look how small these values get. So anything, if you're 4.22 standard deviations away from the mean, there is essentially nothing outside of it. Okay? So this was kind of a tricky problem because it makes you do some stuff that isn't as straightforward as the examples we've covered in class. One part remaining. So which one is it? So we're definitely, it's either going to be A or B, right? Assuming mu is 0, because that's the hypothesis that we're testing. But which of the two is it going to be? Greater than or less than? Because our Z value was positive. So therefore we would expect it to be greater than. Once again, that kind of supports the fact that it should only be a one-tailed test, but excuse me. But we're testing it against the fact that it's not equal to 0, even though that wasn't explicitly stated. On a test, I will explicitly state, all right, test it against the fact that it's less than, greater than, or not equal to. So there won't be any ambiguity when it comes to that. Okay? Any other questions from this assignment? So this one, this one's explicitly stated, right? That one says less than 20. This is out to 4 decimal places. Let's go ahead and just do this one too, just for practice. So we'll just answer this p-value question. So I think the hard part with that number 8 was setting up your alternative hypothesis correctly. Because I'm not even buying into it as of now, even after doing the problem. Right. So our H naught is mu equals 20, or HA is mu is less than 20. So this is step 1, step 2. I'll go ahead and just go through all the steps. What's step 3? What test statistic are we going to use for this?
Z.
Z. Because n is greater than or equal to 30. Now, what I started in class yesterday was talking about the t statistic, so we'll do that again today as well. 4 was a rejection region. We're not given an alpha here in this problem. You guys see that? Right? We're not given a level of significance. So I'm just going to skip 4. Number 5 is assumptions. I'm going to go ahead and assume the central limit theorem because n is greater than or equal to 30. So step 6, I need to find my z statistic and then the p-value. So z equals x bar minus mu over s divided by the square root of n, which is equal to 19.1 minus my mu from my null hypothesis, divided by s that was given to me, 11.3, divided by the square root of what for this problem? 43. N is 43. So let's punch that in our calculators. Notice how I write this out every time? So on the test, don't just tell me z equals, and I want you to write this down. That way if you make a mistake in your calculator, I can still give you some credit for it. Don't just put z equals 1.9, and if it's wrong, then you don't get any credit for that section. Okay? So show me as much work as you can. Show me all the work. So open parenthesis, 19.1 minus 20, close parenthesis, divided by open parenthesis, 11.3, divided by the square root of 43. What do we get here? Negative. Right, everybody does see it's going to be negative because x bar is less than mu. 0.52, right? 0.52. Or just 0.52. So this is a one-tailed test. So what I'm looking for is the area under the curve to the left of negative 0.52. Right? So my p-value is going to equal the probability that z is less than negative 0.52. Which I'll go ahead and just draw a picture. Now this p-value is going to be pretty big, right? I mean, relative to the other ones we've looked at. Because this is only 1/2 of a standard deviation below the mean. So let's go ahead and just draw a picture just to make sense of it. This is definitely not a two-tailed test. So about 1 is going to be about right here. So negative 0.52. It's right there. So my p-value is that region. So it's going to be 0.5 minus whatever it is in this region, which is given to us by the chart. So it's 0.5 minus, not negative 5, 0.5. And then let's go look at it in the book. So find 0.52 in your graph, in your chart. 0.52, 1985. 0.1985. So 0.5 minus 0.1985. That's our p-value. 0.3015. Now we can't do a conclusion. So 7 is since alpha isn't specified, there is no conclusion. We can't say anything about H naught. But more than likely it's going to fail. Or we're going to fail to reject H naught. Because that Z statistic is pretty close to the mean. So we would assume, since our X bar of 19.1 is so close to 20, especially when we look at it relative to the standard deviation, there's not statistical evidence to show that the true mean differs from 20. So we would fail to reject H naught. And we would go ahead and say, we fail to reject H naught, so we're not sure if the true mean differs from 20. Remember, we can't accept H naught. So my answer there says round to 4 decimal places is 0.3015. Whoa. Oh yeah, this is in the Word file. So, compare the p-value with alpha equals 0.05. Which one's greater? The p-value or alpha? Huh?
Alpha?
Alpha is greater than the p-value? No, the p-value is a lot bigger, right? The p-value is much greater than alpha. So remember, we reject H naught if the p-value is less, right? So we reject H naught if the p-value is less than alpha, which means the area of rejection is smaller than the rejection region. We fail to reject H naught if the p-value is greater than alpha. Which that is the case, right? 0.3015 is definitely bigger than 0.05. So there is insufficient evidence to reject H naught, which is the same thing. Very insufficient evidence to reject H naught. And that's a very big p-value. That's like one of the biggest ones we've seen, right, so far. So I would assume that the population mean is very close to 20, if not equal to it. Okay. Let's go look at the book. Let's go finish out 8.4, or 8.5, excuse me, because 8.4 is due tonight, but I pushed 8.5 to be due tomorrow night. So let's look at that example on page 375. The one with the mechanic. So we have to remember to keep this stuff separate. Remember, the p-value and alpha are the same thing because they're talking about areas under the curve. The test statistic and the rejection region are the same thing because they're talking about the z-value that corresponds to the area under the curve. Everybody see the difference? P-value and alpha, would you guys agree that this is two-dimensional? Right? It's area under the curve. The z statistic, this value is a one-dimensional value, right? That is just the value of z on the horizontal axis. So even though both of these are decimals, they really have nothing to do with each other, right? This is an area This is a z-value. Okay, a z-value corresponds to a certain area. This z-value corresponds to this area, being to the left of it. All right, so we have to keep those two things separate. And that's something that I see mixed on the test. Because this is very important for all of this stuff we're going to do for the rest of the chapter. So let me erase that part. So this is our test statistic. Is equal to negative 0.52, but 0.3015 is the p-value. Does everybody see the difference between those two things? P-value is an area. Alpha is an area. Okay? And then I think the rejection region, it said was 0.05, so on a one-tailed test, what was it, like 1.6 something? Right? It was negative 1 point. I think on a one-tailed it's 1.645. Yep, negative 1.645. That's alpha, which would be 0.05. Anything z less than this value is the rejection region. Right? So it's very important that we see the similarities and differences. We see if the test statistic falls in the rejection region, which in this case it doesn't. Another thing that tells us the exact same conclusion is if the p-value, which is all this area, is less than alpha, which is this area, which in this case it's not as well. So the p-test and the rejection region tell us exactly the same thing, it just does it in different forms. Okay? Very, very important that we recognize the difference. And I did see some people mixing this stuff on the test. Okay? And the p-value actually includes alpha, right? It's all of this area out here. So the area for the p-value is definitely greater than alpha, which is 0.05. Okay? All right, so let's go look at 8.5, which deals with the exact same stuff. The only difference now is we're using the t-test instead of the z. Right, we're using the t-statistic instead of the z-statistic because our sample size is small. Now there's two things we have to, two conditions for a small size sample, which this is the exact same box as what was there on for the z-test, right? Everything's exactly the same. The formula for t is even exactly the same. The rejection region, whether it's one tail or two tail, is exactly the same. The only difference is what value it is in the rejection region, right? Because the t is spread out a little bit more. Okay? And then there's two conditions for a valid t-test. The first one's just like all of our other things we've saw. The sample has to be chosen at random. And the second condition for a small sample is the population has to be approximately normal. For large sample, n just had to be greater than or equal to 30, which using the central limit theorem said the distribution would be normal. So the central limit theorem is a lot stronger than this, right? Because the central limit theorem said the population didn't have to have any particular shape. we knew the sampling distribution would be normal. Here we have to assume the population is normal so that the sampling distribution would be normal. So let's do this problem. You'll notice that there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. That is definitely a small sample size. All right, so we're going to use the t-test here. All right, so let's go through and do it. A major car manufacturer wants to test a new engine to determine whether it meets EPA air pollution standards. The mean, what does it say? The mean emission mu of all engines of this type must be less than 20 parts per million. All right? Must be less than 20 parts per million. So the greatest it can be, the biggest value is 20. 10 engines are manufactured for testing purposes, and the emission level of each is determined. The data in parts per million are listed in Table 8.5. Do the data supply sufficient evidence to allow the manufacturer to conclude that this type of engine meets the pollution standard? Assume that the manufacturer is willing to risk a type 1 error with probability alpha equals 0.01. So the null hypothesis is equal to 20. The research hypothesis is that the mean level is less than 20. Remember, the research is equivalent to the alternative, right? So our null hypothesis, so step 1, is that the mean is equal to 20 against the research hypothesis or the alternative hypothesis that mu is less than 20. This doesn't say against the mean for all engines of this type is not equal to 20. Right? Then it would be a two-tailed test. This is definitely a one-tailed. Right? Does everybody agree with that? And the giveaway is, remember, your null hypothesis is equal to almost all the time. And then it's your alternative that's either less than, greater than, or not equal. Okay. So there's step 1 and step 2. Step 3, we can't use the z-test. We have to use the t-statistic. Because n is less than 30. There's less than 30 observations. 4. 4 is our rejection region. What's our alpha here? Alpha equals 0.01. So what is our rejection region? And this is a one-tailed test, so it's going to be t is less than something. We need to go look at our t. Yeah, let's go look at it, though, just to make sure we've got it. So what degrees of freedom are we going to use? Not 19. How many were there? 9, right? N was 10. So alpha equals 0.01. Degrees of freedom equals 9. So, questions? Anybody? No? So, since we're doing a one-tailed test, our value is going to be given to us right here in this chart. So we want alpha to be 0.01, which is right here. And then we go down to degrees of freedom being 9. And there it is. But what's the value of this going to be? Is it going to be positive or negative? Negative because, why? Because it's less than, because it's a lower tail test. The reason I know it's a lower tail test is because this is less than 20. Good job. So t must be less than negative, is it 2.821? So that's our rejection region. What's our assumption here? What do we have to assume in the conditions for a t-test? That what? Remember, what was that second condition we just looked at? The population is approximately normal. Very good. Approximate, but I'll just put approx for abbreviation. So we are assuming that the population is approximately normal. And that the sample was taken at random, but every time we assume that, so you don't have to state it. And I'm not really even concerned that you can state that as much. I'm very concerned about all the other stuff, though. So number 6 says, what's our step 6? Calculate the t-statistic. So now I'm finding my t-value from the problem. So t equals, it's x bar minus mu over s divided by the square root of n. It's the same thing as the z. And I put mu naught because it's the specific mu from the problem. So let's go back to the book, 375. We're not given an x bar and an s yet. We're still not. Degrees of freedom is 9. So there's our t value, negative 2.821. It's negative because our alternative was less than. If this would say greater than, then this would be a positive number. If this was not equal to, then we would have a two-tailed test. And this number would actually be pushed a little bit farther out, right? Because we would have found 0.005 on the chart instead of 0.01, because we'd have to divide it in half. All right, does it give us an x bar and an s? Oh, it doesn't. We have to find it. That's a good practice. Let's go ahead and find our x bar. Or we can just punch that into the calculator, into what we did in the first couple chapters. So that's what I'm going to do. I'm just going to put this into my data. And this will be a nice little review of that as well. The other ones where the sample size was huge, it gave us x bar and s. Here, since the sample size is so small, it wants us to do it. But I'm not going to do it by hand. I'm going to punch it into my stat commands and let the calculator do the work for me. So remember, what you do here is I hit the data button on this calculator. I go data, and I already have some data put in there from before when I've done it. So let's put in our 10 data points: 15.6, 16.2, 22.5, 20.5, 16.4, 19.4, 19.6, 17.9, 12.7, and 14.9. Okay, there's my 10 data points. So now I'm going to hit the second stat button. So I'm going to go second stat. One variable stats. We haven't done any two variable. That's where we're putting in two different data points for each observation. So maybe if we were doing height and weight of 10 individuals, that's what two variable stats is, which is something you do in Stat 313. I'm doing the data from level 1, and I'm doing frequency of only 1. So let's do a calculation. There's n is 10. There's my x bar. X bar is 17.57. So we have 17.57 minus 20 divided by something over the square root of 10. Which one of those is my standard deviation? Is it S or sigma?
S.
It's S. It's always the S value.
How many decimal places should we round on that to?
Good question.
Because I've done them both, and sometimes it's 4, sometimes it's 3, sometimes it's 2. It just depends what the computer, I guess.
Wants, right. And I'll specify, but usually if it's not specified, you go to 2. Because that's what our chart gives us, right, is to 2 decimal places. Not the T chart, but the Z chart does. So I like to go to 2 myself. The T chart actually gives us out to 4 decimal places, right? But I'm just going to go to 2. That's fine. 2.95. And on a test, now, my MATLAB might count you wrong, but as long as you're showing me all your work and I see that you're rounding it to 2 decimal places, I mean, I'm going to give you credit for that stuff. That's what matters, right? Is that you know the process. If you're off by one digit because of rounding, that's not nearly as big a deal. Now, if you put your S up here and your X bar down there, now that's a big deal, right? That makes a big difference. So what do we get here for our T statistic? So it's going to be, I have 17, so I'm going to go ahead and clear out of there, clear. 17.57 minus 20 is that, and then I'm going to divide it by, open parenthesis, 2.95 divided by second square root of 10. Always press to the right there so we get outside the radical, and then close the parenthesis. Negative 2.6. 0, right? Yeah. So what's our conclusion? When we compare our T statistic to our rejection region, does it lie in the rejection region? No, so therefore we can't reject. There's insufficient evidence to reject. We fail to reject. We can't reject any of those statements. You know, I like the fail to reject. So fail to reject H naught. So we would conclude that the mean emissions for these engines is very close to 20. It's not statistically significant to say it's less than 20. That's it. So really the only new stuff is right here, right? Is step 4, is calculating the rejection region. I mean, the way you find the test statistic is exactly the same way. So really for 8.5, the only difference is this value of your rejection region is going to be a little bit different. And I could go in and find the p-value, but the p-value for small samples, the way our chart's set up, you can't really do it. You know what I mean? I can go and try and look for this number in the chart somewhere, depending on my 9 degrees of freedom. But it'll only ask you for p-values on large samples because of the way the data is shown to you. In the T-chart, you know, you can't explicitly find it. Let me show you what I'm talking about. Now, if I asked you to find the p-value of that number, I'd have to go find 2.6 at 9 degrees of freedom. So it would be somewhere in between these two numbers. Everybody see that? My 2.6? So it'd be somewhere between 0.025 and 0.01, but I can't pinpoint it because of the way this information is given to me.
There's actually a couple problems on the homework for 8.5 where it asks you specifically for the p-value when it's not in the chart.
Really?
Yeah.
Okay.
So
So you got to kind of guess or what?
it
Basically.
expects a specific answer. It says use technology to find it, so I don't know how to find those.
Okay.
I think I hit that one,
Well, let's go
and I
look at
tried to add those two together and then divide by 2, and it didn't work.
See that because it's not symmetric, right?
Yeah.
Yeah, because when you get to the edge of a tail, right? If I'm out here, that is not symmetric. Those two halves right there, right? So I can't just take the number in between and divide it in half. It doesn't quite work that way. So let's go look at. You know what it might do is have you use StatCrunch for that. But I think so. So let's finish this section, then we'll go look at the homework. On a test, I wouldn't do something like that. You just would look at the rejection region. But it would have to be somewhere, the p-value would definitely be somewhere between 2.262. Well, it'd be, since 2.6 is between these two values, the p-value would be in between 0.025 and 0.01. Probably somewhere around 0.018 or so, give or take. About 1.8%, since it's between 2.5% and 1%. Okay, so let's go back, make sure we come to the right conclusion from the example. So there it is. So our rejection region is out there. Here's our t value that we came up with, right? Negative 2.6. We have to assume that the frequency distribution of the population is approximately normal, right? That's one of our conditions for using this small sample test. And get to the next. So finally, our answer is, since the calculated t falls outside the rejection region, the manufacturer cannot reject H naught. There is insufficient evidence to conclude that the mean is less than 20 parts per million. All right. All right. Are you satisfied with the reliability associated with this inference? The probability is only alpha equals 0.01 that the test would support the research hypothesis if in fact it were false. I would be pretty conclusive with this because that's a pretty small alpha. If it was 0.1, I wouldn't be very convinced. But 0.01, I mean, that's a 99% chance that we got it right and a 1% chance that it was type 1 error. So I would be pretty satisfied with the reliability myself. Oh, and here we go. Here's the exact question I was talking about. They even use the same numbers. Find the p-value for the test described. So it wants to know the p-value here. It's exactly what I was talking about. So let's find the p-value associated with it. So now we're using a t-statistic. I'm going to draw it a little bit more flat because that's what happens with t, right? It's a little flatter. So here's 0. Here's negative 2.6. So the p-value's right there, right? It's that area. Does everybody agree with that? And my degrees of freedom was what? 9. Good. The test of example 8.7 was a lower tail test. Since the value of t computed from the sample data was t equals negative 2.6, the observed significance level for the test is equal to the probability that t would assume a value less than or equal to 2.6, which is the area under the curve to the left of 2.6. If in fact H naught were true. This is equal to the area in the lower tail of the t distribution. And they even have the same picture that I just drew. All right? So there it is. One way to find this area, i.e. the p-value for the test, is to consult the t-table. Unlike the areas under the normal curve, table 6, excuse me, not 4. Table 6 gives only the t-values corresponding to certain areas, right? Only the ones for 0.1, 0.05, 0.025, 0.01, and 0.005, along with 0.001 and 0.0005. Therefore, we can only approximate the p-value for the test. Since the observed t-value was based on 9 degrees of freedom, we use that, df equals 9, rho, and move across the row until we reach the t-values that are closest to the observed t equals negative 2.6, which is what we've already talked about, right? Of course, we ignore the minus sign because the area to the left of negative 2.6 is equal to the area to the right of positive 2.6, right? Which is what the table gives us. So we've already talked about this. We know our p-value needs to be between these two. Somewhere between 0.01 and 0.025. Because it was 2.2 and 2.8. Since the observed t-value falls between the p-value for the test lies between 0.01 and 0.025, which isn't anything we haven't already talked about. Right? A second, more accurate way to obtain the p-value is to use a statistical software package to conduct the test of hypothesis. Both the test statistic, easy for me to say, and the p-value are highlighted on the mini-tab printout. So we don't have a mini-tab printout. You can see the actual p-value of the test falls within the bounds obtained from Table 6. Now, I did this in StatCrunch a while back, so let me go do it again. And then we'll go find it. Small sample inferences, this information. What can be done if the population relative frequency distribution departs greatly from normal? So what if our second condition wasn't met? What we'd use what's called a non-parametric statistical method that we're not going to cover, right? So it is possible to still do a small sample hypothesis test even if the population isn't normal. We're not going to deal with it, but it is possible. I mean, that's something you might have to do someday in the real world, all right? Maybe you only have 8 samples and you need to do a hypothesis test where the population was skewed one direction, all right? So now you at least have the tools. You might not understand exactly how to do this method, but you at least know that you need to do that method to find it, all right? Which, remember, the real world's an open book, right? You'll always have the book open. All the information is there for you to find. You just have to know where to look and how to sift through it, right? That's the hard part. I mean, in the internet age, they call this the information age. It's not from lack of information. It's being able to sift through it all that's the hard part. So let's go do one of these on our homework. Continue. No, not managed, dang it. Course tools. 8.5 preview. Go. So these are all in the textbook, right, from this problem. All these numbers are actually contained in the chart. The 2.718, negative 1.476, they're all in there. Do you remember exactly which number it was? 5. Okay.
And it's part C that asks for the p-value.
Okay. Let's just go and see if I can find it in StatCrunch. Oh, you can even change that. Confidence interval. Build. Oh, and then you can even build the data. Right, let's go see. So it is listed in there. I just got to have the right data. All right. So let's go ahead and just do this problem then. So in bonding teeth, so orthodontists are gluing teeth, I think, to the gum. I'm not really exactly sure. When bonding teeth, orthodontists must maintain a dry field, which means your gum basically has to be dry, right? It can't be wet to get a good bond. A new bonding adhesive has been developed to eliminate the necessity of a dry field, which is nice. However, there is concern that the new bonding adhesive is not as strong as the current standard. Test on a sample of 8 extracted teeth So there's our n, right? Let's go back to here. I know we're going to use the t-statistic. Right. So n equals 8. I'll just go ahead and make note of that. So n is 8, so the degrees of freedom will be? 7. Right. Right. On 8 extracted teeth. And a new mean breaking strength of x bar equals 4.65 and a standard deviation s is 0.48. So that's what we use when we're finding our test statistic. Orthodontist wants to know if the true mean breaking strength is less than 5.16. So that's what they're researching. So what's my null here?
It equals 5.
Equals, right. Mu is equal to 5.16 against the alternative that it's less than 5.16. Step 3, we're definitely going to use the t-stat or the t-test. The rejection region, alpha is what? 0.01. So that was the thing I just had up here on. So t has to be, oh no, my degrees of freedom is going to change. Going to change it. Okay, so what's our set A? I just wrote it up here. It's going to be this one, right? Yep. Equals the 5.16 versus the alternative that it's less than. So that's definitely part E. Okay? So now let's compute T. So that's going to be x bar minus mu over S. So I'm not even setting up the rejection region yet. So 5 is the pop, is approximately normal. So step 6 is the t-statistic, so it's x bar minus mu over S divided by the square root of n. So my x bar that we're testing is 4.65 minus 5.16 divided by S, 0.48, divided by the square root of, not 7, of 8, right? Divided by the square root of n. Everybody realize this is going to be a negative value? Which is important since our alternative is less than. So we would expect our t-statistic to at least be negative. Divided by, open parenthesis, 0.48 divided by second square root of 8. Negative 3.01
We're rounding to 3 decimal
to 3?
Yeah.
Oh, it does say 3. 3.005 then. Good job. Way to read the instructions. So negative 3.005. Is everybody following right now as of this? Is this making sense? Good. Now here's where we have to calculate the p-value. So let's look at the textbook, which I don't want to close this homework assignment. So I'll pull it up over here. So we're only looking at degrees of freedom being 7. And then we're looking for our test statistic, ignoring the negative, which is going to be in between these two values, right? Right. So we have an idea of what it should be. We know it has to be between 1% and 0.5%. Does everybody see that? Probably pretty close to 1% though, because 3.005 is really close to 2.998. I'm looking, yeah, 2.998 is for 7 degrees of freedom. But what I want to do now, so let me get to the right place right here. And it says round it to 4 decimal places on. So I know where it's ballparked in between. It just says use technology. I'm not, and your calculator. Doesn't give us anything like that. Because I'm not sure I want to go through and have you guys learn a whole nother statistical software to answer this one question. So let's see if we can figure this out. Okay. So, here's where I went. So I opened StatCrunch, and I'm still not even sure this is going to work, but let's look at it. So you go to Stat, T-Stats, one sample with summary. So we're not worried about putting the data in. And look what it tells us. So it wants us the sample mean, which is 4.65. The sample standard deviation, which is 0.48. What's the sample size? 8. Whoa, not 89. Let's set up our hypothesis test. It was mu equals what? 5.16. Against mu is less than 5.16. What was our alpha?
0.01.
All right, so that would be what would be the confidence level? Remember, what's the formula for it? It's 100. 100 times 1 minus alpha percent. And what was alpha?
0.01.
0.01, so that's going to be 99%, right? Okay. Or 0.99. Let's see what it tells us. Upper limit, lower limit. What's this got over here? Standard error. That number's a little too high on lower limit, upper limit. So that's not it in StatCrunch. So let's see if we can find another technology that'll do it for us. Because it's definitely smaller than that, right? That's not the right thing. It's got to be somewhere between 1% and 0.5%. So that wasn't it. I don't know why it doesn't show. Oh, there we go. No. That's all the for T statistic. Oh, there we go. I'd like to find a, because I don't want to go through and show you guys how to put it in a mini tab. I mean, we could. Oh, here we go. Look at that. Let's see if this works. What's our degrees of freedom?
7.
7. And our t-value we found was, and it doesn't matter if you do negative or positive, right? And look at that. That is definitely between 1% and 0.5%. Right? You guys see that? So you're welcome to use this right here. It's the Daniel Soper. So write this URL down. Here, let me copy and paste it into that Word document so it's a lot bigger. I think this is a lot easier than having to teach you Minitab in a short period of time. Now on a test, I wouldn't ask you for a p-value you couldn't readily obtain. So there it is right there. danielsoper.com/statcalc3/calc.aspx $ID = 8. And all I Googled, right, all I typed into Google was p-value for t table. That was it. And this is the thing that came up. Okay. So let's go make sure it's the right number. So is this a one-tail or a two-tail? Which you'll notice the two-tail is just that thing times 2 is how you get that. So it's this number, 0.0099, which we expected it to be very, very close to 1% because this number was so close to 2.995, right, which is what was in the table. Let's see if we get it right by putting that. Okay? So I think that's a much easier thing to use. It's really a pretty neat page right there. So it gives you the one-tailed and the two-tailed right there in front of you. Once again, like I was just talking about, the information's out there. It's just sifting through it, which is kind of what I had to do. Okay. And then give the appropriate conclusion. What's the relationship between the p-value and alpha? Which one of these two things happens? Is our p-value less than alpha or is it greater than alpha? It's less than slightly, right? It's very, very close, but it's still less than. So therefore, our conclusion is we reject H naught. There is sufficient evidence to indicate the mean is less than 5.16. And there we go. So I'm glad you brought that up. Which that would have been something I covered on Monday for sure at the beginning of class. But now we've hit it. So now, the nice thing about this page is you can do it for anything now, right? You can make degrees of freedom 15 and your t-value be 2.713. There it is. It gives it to you. I bet you can even go find this for the z's as well to make your life a little easier, right? Which I would say, use it as a tool, not as a crutch. If you understand how to do it, you're welcome to use something like this to save time. Do not use this if you don't understand how to do it. Don't let this be your only method to do it, right? To me, it's almost more important that you can create this picture than tell me exactly what that p-value is, right? Because this picture really tells me you know what the heck's going on. I don't even really care what the number is, but the fact that you can give me the right t statistic and color in the correct tail with the right degrees of freedom, that's really all I need. Right? That shows me that you understand what the question is telling you. Okay? There we go. All right. So let's go look at the last section, which isn't bad at all. It's just proportions. So to me, it's actually the easiest of the three of the testing that we've done. Because it's back to using the z-score because this only works for large samples. I've got to close this page up. So chapter 8, select all. The last section. Notice how this is just large sample hypothesis about a population proportion. So now, rather than testing mu, right, rather than this being mu, it's going to be p. And other than that, it follows along the exact same set of steps. We do the same type of testing. Everything's the same except for our initial hypothesis. So here we go. Large sample test of hypothesis about a population proportion. Inferences about population proportions or percentages are often made in the context of the probability P of successes for binomial distribution. Remember, this is usually qualitative data. Something is, there's a new, so this example talks about detecting breast cancer. And they call, so we first view this experiment as a binomial one. So let's read the experiment. Consider, for example, a method currently used by doctors to screen women for breast cancer. The method fails to detect cancer in 20% of the women who actually have the disease. So if it measures a woman that actually has breast cancer, it'll give you a false negative 20% of the time. Okay? Which is not good, right? That's really bad. That's way worse than, this is definitely a type 1 error, right? That's a lot worse than telling a woman she does have breast cancer when she doesn't, which is really scary for her, but you'd rather be told you do when you actually don't than to not be told you do when you do have cancer, right? So that's the type 1 and type 2 errors, right? Suppose a new method has been developed that they hope will detect more accurately. This new method was used to screen a random sample of 140 women. So there's our N. Our N is 140. So that's a large sample. So we don't have to worry about degrees of freedom here. I'll just leave the numbers up here. So right away, before I even set up my known alternative, I know I'm going to use the t statistic because n is greater than or equal to 30. So right away I know that. My n is 140. Of these, the new method failed to detect cancer in 12 women. Does this sample provide evidence that the failure rate of the new method differs from the one currently in use? What does this word differs tell us about the alternative?
Not equal.
It's going to be not equal to, right? Because it wants to know whether it's more or less than. So one of them is going to be P equals something. The other one's going to be P not equal, whatever that is. How do I determine what this is? Well, actually, it's given to us right here. This 12 out of 140 is how we're going to come up with our sample proportion. Does that make sense? That's going to be our P hat. So this is what we're testing. P equals 0.2 against it not equaling 0.2. Three is the Z statistic. Do we know the rejection region yet? Has it been given to us? Let's look in here. Do we see any alphas? Do we see anything that says alpha equals or? It doesn't. Yeah, it doesn't give it to us till later on. Well, it does say 0.05 on the next page, right? But it doesn't tell us right here. So I'm just going to skip step 4 as of right now. Because we haven't been explicitly given it. 5, we're going to use the central limit theorem. That's our assumption. So 6, let's figure out our Z. Which I can find the test statistic before I do the rejection region. Right, so let's find, now what's our formula for the Z on the proportions? This is kind of the new stuff. It's right there. Let me zoom this in. Recall that the sample proportion p hat is really just the sample mean of the outcomes of the individual binomial trials, and as such is approximately normal, according to the CLT. Thus, for large samples, we can use the standard normal z statistic. So this is the new stuff. P hat minus P naught over the standard deviation of P hat. So what I want to do now, let's go look at, oh, it's down at the bottom of the page. So let me roll down and kind of skip the answer real quick. And let's just get our formula. There it is. So Z equals P hat minus P naught, which is the same thing as mu naught, right? It's whatever our null hypothesis value is, divided by the standard deviation of P hat. Now, this, I think it would make more sense for this notation to be the standard deviation of P naught, but because notice what happens here. We're using P naught and Q naught, not P hat and Q hat. Everybody see that? But you'll be given that formula on the test. You won't have to memorize that. But this, if this would have said P hat, it would be 0.086, and then this would be 1 minus 0.086, but that's not what we're testing. Right? We're using this value that goes there. So the square root, so this is equal to, what is P hat for this particular problem? How did they come up with this number? Right, because that's what they gave us in the previous, right, in the first paragraph. It said the new method was correct, or was incorrect, 12 out of 140 times. 12 out of 140 is 0.086. So this is going to be 0.086 minus P naught, which is whatever this value is, divided by the square root of 0.2 times Q. And how do they come up with Q? 1 minus P, the complement, right, of P, divided by the square root. Oh, see, I put too many square roots in there. Yeah, be careful not to put, if you have the first radical go over the denominator, make sure you don't put a double radical in there. And then let's put all this in the calculator and make sure that we come up with that number. So I have 0.086 minus 0.2 divided by, open parenthesis, 0.2 times 0.8 divided by second square root of 140. Out and close parenthesis.
Doesn't that have the square root over all of it?
It is. Yes. Yeah, see this line? Now, you could write it as the square root of this piece divided by the square root of this piece, but you have to make sure that this first square root doesn't go over the 140. Right? You want to make sure that you don't double square root 140. And then hit equals. Oh, and I didn't put the whole thing. Dang it. And I made a little mistake with my order of operations.
I got 3.37.
No, what I did is I didn't put these two under the radical on my calculator. So I had an issue. Right? So that's just something to pay attention to. The nice thing is you don't have to put this stuff in parentheses under here. But after you do this, then you come up with negative 3.35. Equals negative 3.35. But I can't make a conclusion yet until I know alpha. Everybody see that? I could come up with a p-value and say that, But I need to determine an alpha. I have to set a rejection region, which was given to us as, oh, and then it does our stipulations to make sure N naught and Q naught, N of P naught and N of Q naught are greater than 15, which basically just verifies that our sample size is big enough. Right? Okay, so what was our alpha? Here it is right here. So we're going to let alpha equal 0.05, and this is a two-tailed test. So our rejection region is going to be the absolute value of Z greater than, and then let's go look at that chart. Well, I guess I'll spill the beans for you guys. I will include this chart on the test. All right? You will have this chart. Okay? That makes life a little easier. So which one of these are we going to get? 0.05 for a two-tail right here, right? So the absolute value of Z better be greater than 1.96. Is the absolute value of negative 3.35 greater than 1.96? Yes. You guys agree with that? The absolute value of this number is greater than 1.96? Or is the positive equivalent of 3.35 greater than 1.96? We would say yes. So we would reject H naught. Now, would you conclude that the proportion is less than or greater than 0.2? Because we only tested that it was not equal to. It'd be less than why? Well, yes, that's part of the reason to think about it, but it's because this number is negative. So it's less than the mean. So we would expect the true proportion to definitely be less than 20%. So this cancer detection works, right? It's wrong, less than the previous method, which is good. So we would reject H naught and conclude and accept HA, but we would even go a step farther and say it's less than 0.2, not just simply not equal to 0.2. Okay? So 382. So we would reject the null hypothesis, concluding at the 0.05 level of significance that the true failure rate of the new method for detecting breast cancer differs from 0.2. Since p hat is actually equal to 0.086, or about 8.6%, it appears that the new method is better, i.e. a smaller failure rate, than the method currently in use. To estimate how much better it is, or the magnitude of the failure rate, a confidence interval could be constructed. The test of hypothesis about a population proportion P is summarized in the next table. You notice it looks exactly like the Z, the large sample mean hypothesis testing, the small sample mean hypothesis testing. Looks just like this. Right? So there's step 1, there's step 2, there's step 3, there's step 4. The only difference here is finding the Z. The formula is a little bit different because the standard deviation is a little bit different. This is really the new stuff is right here, right? So sigma of p hat is equal to the square root of p naught times q naught divided by n. But it still has the square root of n in it, just like our Z statistic did. The difference is it square roots this piece as well, right, where our other stuff didn't. Because P, the reason it square roots this piece is because the variance was defined as P times Q, remember? And the standard deviation was the square root of P times Q when we first looked at this stuff. That's why this is the standard deviation. That's why we're square rooting the numerator as well. Because the variance was PQ, so the standard deviation has to be the square root of PQ. Okay? Conditions. What's going to be my first condition? What do you guys think? For a valid large sample hypothesis test.
Samples taken at random.
That it has to be taken at random. My second condition, that the sample is greater than 30. Or n times p and n times q are both 15, so that when you add them both together, you get 30. So basically, there has to be at least 15 successes and at least 15 failures, because that means you've had 30 observations. Does that make sense? So that's where this 15 comes from, because it's exactly half of 30. Okay. P-values are exactly the same. All right. So let's take 5 minutes, and you guys do this problem. Right here. So I want you guys to do a large sample hypothesis test for P. A large sample hypothesis test for P. So first thing, set up your H naught, your HA. So read through the problem and determine it. So right here, this middle sentence tells us our null and alternative hypothesis right there, right? .05 is our value, right? We have to figure out the operators. Raise your hand if you're having trouble. Touch your Give it to you right there. So it says 10 out of 300 is how you find your p-hat. Here's our last example of the semester. All right? That's new. Then we'll go ahead and find the p-value too at the end. But I'll give you guys a couple more minutes to work on this. What you guys got for your rejection region? So first I'm going to find p hat, which is 10 over 300, which is 1 out of 30. Do it out to 3 decimal places. So there's p hat, so I need that to find z. What you guys get? It's definitely going to be a negative.
1.32.
I had 1.35, which you probably have 1.32 because you probably only did this to 2 decimal places. Is that right?
I did it out to 4 decimal places.
Oh, you did this one to 4? Well, that's why it's different. Yeah.
What?
Yeah. Question?
0.05 on the bottom.
Uh-huh.
It says to find the t statistic, you're doing
T,
sigma.
Z.
Yeah, I'm sorry.
Yeah. Yeah, this is the standard deviation of p hat, which is defined as the square root of p naught times q naught divided by 3 by n.
So wouldn't the
Now, you're going to be off by a little bit if you didn't use exactly 0.033 because this is what we call a repeating decimal. So really, to be exactly correct, you could put in 10 over 300 instead of the decimal right there, and you use all the decimal places. But either way, you're going to come to the same conclusion. Using 3 decimal places, I came up with negative 1.35, where no matter how you rounded it, you came up with a number that was around this, right? But in any case, no matter what, does it fall in the rejection region? No, not even close, really. So our 7, our conclusion is fail to reject H naught. Because what's the p-value here? Let's just ask that question. P-value, which is going to be equal to the probability that z is less than negative 1.35. So the p-value is going to be equal to 0.5 minus the probability that it's between 0 and 1.35, which is 773. So 1.35 right there, 0.4115. equals what? 0.0885? No, is that what it is? Which is definitely greater than alpha. So both, whether we use the p-value or we use the z statistic, they both get rejected. Right? So our answer here is we failed to reject H naught. There is not sufficient evidence to conclude that less than 5% of the batteries, or whatever the product is, I think it's batteries because that's what it has in the picture. Question?
My order of operation has to be wrong, but I'm coming up, I've got the same one.
Yeah, right. Let me go look at it. So we come up with that as our rejection region, negative 2.33.